Hello and welcome to KringleCon 3. In this talk I'm going to tell you some random facts about something called a Mersenne twister. But first of all, let me introduce myself. Hi, I'm Tom Liston. I'm new this year to Counter Hack Challenges, but I'm not at all new to security. In fact, I'm kind of old. I've been around for quite a while and I've done a number of things in the field of security. You're listening to me today because you decided to click play on this video. Everybody makes bad choices every now and again, so don't feel too bad about it, but realize that it's on you. Let's talk a little bit, begin all of this, let's talk a little bit about randomness in software. Anybody who's ever used a computer for any period of time has had, at some point, the computer freak out and start doing weird things on them, seemingly random things. And now, while that may have happened, it's not because of software. Software is not random. Software is, by its very nature, incredibly deterministic. It does exactly what it's programmed to do. So what we find is that generating true randomness in software is actually incredibly hard. While you can do some things with hardware that will allow you to access a source of true randomness, most operating systems and most computers probably don't have a good way to access a true source of hardware randomness. And so when developers are creating programming languages, one of the things that they try to do is they try to be very OS or very system agnostic. So they don't really have any sort of good cross-platform means by which they can generate true randomness or access hardware that would give them access to true randomness. So most software languages, most programming languages, have some sort of pseudo-random number generator. Well, what is a pseudo-random number generator? A pseudo-random number generator is pretty much exactly what it sounds like. It generates numbers that appear to be random, but that actually are very deterministic in nature. And that sounds like a pretty perfect match for software, which, as I said, is in and of itself pretty much deterministic. The output of a pseudo-random number generator is generally determined by an initial value, oftentimes called a seed. And that you can generate that seed value itself somewhat randomly by, oftentimes people will use the current time of day or the number of milliseconds since the machine started. But here's the thing. No matter how randomly you may generate that seed value, if you use the same seed value again, you're going to get the same string of random numbers out of your pseudo-random number generator. Remember, pseudo-random. It's an algorithm. Same input, same output. Most of the time, statisticians and people who care about this kind of stuff will not talk about what makes a pseudo-random number generator good. They'll talk about the kinds of problems that makes a pseudo-random number generator bad. And one of the biggest ones is something called the period of the pseudo-random number generator. That's the amount of numbers that the pseudo-random number generator algorithm can generate before it begins generating the same sequence over and over again. Some pseudo-random number generation algorithms have a period that's dependent on the seed, and that can be really bad, because if you pick the wrong seed value, either accidentally or if you happen to choose one of them because that's the number of milliseconds since the machine started off, you can end up with some really bad random numbers being generated. Bad from the perspective of being statistically bad. Now, there's a ton of other tests that get done when they're trying to look at the statistical soundness of a pseudo-random number generator algorithm. You want your the numbers that are generated to be distributed uniformly. That means that you want this, you want big numbers and small numbers all mixed up if you're creating numbers within a range. You don't want successive values to be correlated in any way. So meaning you don't want, like, if it generates the number 7, you don't want it to always after that generate the number 12. Or you don't want it to always generate a small number, then a big number, then a small number, then a big number. All of these things play into what makes a pseudo-random number generator good. And there's a ton of other statistical tests. This is not something that I want to get into. I hated statistics in college. I'm sure you did too. If you're a statistician, I apologize, but hey, we're going to move on. So let's talk about the current state of pseudo-random number generators. First of all, there are a ton of different algorithms that can be used as a pseudo-random number generator. Up until 1997, most of the pseudo-random number generators that were in programming languages were of a type known as a linear congruential generator. Those were horribly bad from a statistical perspective. And in fact, they were so bad that they really couldn't be used when you were doing some kind of heavy-duty research that required random numbers to be used in your research. In 1997, Makoto Matsumoto and Takuji Nishimura developed a new class of pseudo-random number generation algorithm called the Mersenne twister. We're going to talk a little bit about where it got that name from in a bit, but understand that this new type of pseudo-random number generator, first of all, is now the most widely used implementation of pseudo-random number generators in software. And in fact, there's a specific version of that algorithm called MT19937 that is absolutely the most widely used version of that Mersenne twister algorithm. What's nice about the Mersenne twister is that it avoids all of those statistical pitfalls that keep statisticians up at night. It has, first of all, it has a huge period. The name Mersenne twister, the Mersenne portion of that, comes from the fact that the period of the pseudo-random number generator can actually be set. And it's set based on a class of prime numbers known as Mersenne primes. So for example, the period for the MT19937 Mersenne twister is based on the prime number that is 2 to the 19,937 minus 1. Now let's just take a look. Here is that number. It's a huge, huge period. Just for comparison, that's a number that is about 4.3 times 10 to the 5,921st power times the number of atoms in the known observable universe. That is a big, big number, and it gives the Mersenne twister an enormous period. That's the amount of numbers that it can generate before it will begin generating the same sequence again. So in addition to having a huge period, the Mersenne twister also avoids all of those other, or at least most all of those other statistical pitfalls. It passes almost every test for statistical randomness. And what's really, really nice about the Mersenne twister is it's actually relatively straightforward to be implemented in software, and it works relatively quickly. Probably the most important point, though, for those in the open source software community is that the Mersenne twister MT19937 is not encumbered by any kind of patent. And because of that, it's been adopted in dozens and dozens of different open and closed source projects. Some of the ones you might be familiar with are things like the language Python. The random number generation within the language Python is based on the MT19937 Mersenne twistor pseudo-random number generator, as is the pseudo-random number generator in Pascal, PHP, Ruby, Sage Math, Excel. Dozens and dozens of other software projects use this pseudo-random number generator. The MT19937 pseudo-random number generator, as I said, is considered to be statistically sound when it comes to the generation of pseudo-random numbers. But don't mistake statistically sound for secure. And let's talk about why that is. What it means to be secure is very different from what it means to be statistically sound in the generation of random numbers. What if I told you that simply by having access to a few hundred recent values from a pseudo-random number generator in a language like Python, you could then predict all of the upcoming values with 100% accuracy? That sounds crazy, but let's talk about how it happens. The 32-bit version of the MT19937 pseudo-random number generator keeps track of its current state with an array of 624 32-bit integers. That's how it keeps track of where it is and what it's going to be outputting. It goes through that list of those 624 32-bit integers, pulls them out one by one, and then hands them back to the user as the pseudo-random number after it's been pushed through what's called a tempering function. And this tempering function is designed to make the output more statistically well distributed. And this is part of the algorithm that was developed back in 1997. The really big important thing here is this. Everything that tempering function does is reversible. And we're going to talk in a minute about why that's very, very important. So once it's gone through all of those 624 numbers, it's pushed them all out to the user through that tempering function. It then uses a different function called the twistor function, which is actually a linear feedback shift register function. And it goes back to then pulling numbers off of that array again, pushing them out through that tempering function out to the user. Now I said that it was important that that tempering function was reversible, and here's why. If the tempering function is reversible, we have the potential to recreate that state array within the MT19937 pseudo-random number generator simply by taking the last 624 random values that were given, running them through a function that reverses the effect of that tempering function, and then stuffing those untempered values back into an array of our own. We can then use that array in our own MT19937 pseudo-random number generator and start generating random numbers using that. And what we'll find is we're generating the same random numbers as the original random number generator. We have, in effect, cloned the random number generator. Now, I know what you're thinking. We don't have to hit this at exactly the right time, right before that twistor function is being used. The reason being is because that's a linear congruential shift register kind of function, it actually works cyclically on this array, and we don't have to hit it at the right time just because of that. You're going to have to trust me because that's the case, because the mathematics involved require a whole lot more time than I have time to explain here. Just so you can see how all of this works, I've made some Python code available to you. It actually uses a created class for an MT19937 pseudo-random number generator to clone Python's built-in random number generator and displays the contents side by side on the screen for you. I've given you the GitHub repository for it. It's on my GitHub repository. You can go and grab the code. You can import it as a module and play around with this kind of stuff yourself, or if you just run the code itself, it'll actually do a demonstration showing you it cloning the output of Python's pseudo-random number generator, the 32-bit version. If you want to use it on your own and try to clone a random number generator in Python or in other languages, understand this. What you're going to need to figure out is how does that language or that application create other types of values. So yeah, if it's just giving you the 32-bit integers, that's pretty easy to do. But what if they're talking about floats? How does the application use the output, the 32-bit integer output from the MT19937 pseudo-random number generator? How does it use that to create those floats? Or how does it use it to create numbers that fall within a specific range? Or how does it use it to create 64-bit integers? I will tell you this, it takes a little bit of looking and a little bit of examination, but you can usually figure out how the application is using those 32-bit integers to create those other types of numbers. Remember, most programs, and especially most programming languages, are very concerned with speed. And so they're going to use potentially the simplest method possible to take, for example, 32-bit integers and make a 64-bit integer, or take a 32-bit integer and turn it into a floating point number. So given that information, given that kind of background method of thinking, they're going to be doing something as quickly as possible. You can usually figure out what it is that they're doing. So just to wrap things all up, remember, randomness in computing is a whole lot harder than you'd think. Remember, statistically sound randomness isn't necessarily secure randomness. The most widely used pseudo-random number generator out there today, MT19937, is actually, while it's statistically sound, is horribly insecure. It's used in dozens of applications and programming languages, Python, Ruby, R, PHP, Excel, etc. And it's something that is just begging to be exploited. So if you have any questions, you can email me at tliston@counterhack.com. Once again, up on the screen, you'll see the location on GitHub where you can go and download the Python code that demonstrates this. Also, finally, one final thing is my Twitter handle is @tliston. So thank you very, very much for attending the KringleCon talk today. And I hope you have a wonderful, wonderful holiday season. Thank you. Ho, 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 ho.